Logic Design, Chapter 4, Lecture 5. Right. So, in the first three chapters, we have seen how we can use binary numbers, logic gates, arithmetic operations, algebraic manipulation, and kernel maps. These are all actually the foundation of the logic design. Now, from this point on, we are going to use that knowledge that we have gained in these three chapters, and we are going to use as an application wise for example, analyzing the gates or designing circuits, finding out outputs and simplifying it, and so on. Now, we'll start with chapter 4, and which we will talk about combinational logic. Now, what is combinational logic? Combinational logic, it's actually you have set of inputs that we are considering that are fed in to your system. Let's say A, B, C. I'll say comp logic over here. And that combinational logic, it's actually producing set of outputs. Okay, there's no feedback over here, no clock, nothing. So we just have the gates. And whenever the inputs are inputted in, it processes the data, and then we'll have the outputs. This is what we are going to see in this chapter, and we are going to see different types of combinational circuits that can be used in logic design. All right, so what is the design procedure for combinational logic? First, we have to specify what the system is going to do. Okay, we have got three inputs, and when we got these inputs, it will do some operations. If you do remember from the previous chapters that we have talked about, like flight seat reservation, that was a typical combinational logic example. So there are specifications that we have to book two adjacent seats. That is the specification. And we have to formulate it. So in order to formulate it, we can derive a truth table, define the relationship between inputs and the outputs, because this is unknown, and this is what we are going to find out. And once we formulate it, we can take that truth table and merge it into a Carnot map or maybe an algebraic equation. And then we can use algebraic manipulation or simple Carnot maps and optimize it to have minimum number of gates, minimum number of literals. Then we can take this further and we can do a technology mapping depending on the application or the hardware that we are going to use. We have to map it. So we have to create a netlist and we have to map it. So in order to confirm the operations, we have to do a verification. Now we have to verify the correctness of the final design. So we check with the LEDs, switches, or with the set of inputs that we are. You can use a logic analyzer and find out what will be the output over there. Now, if we are using FPGAs, then we have to investigate how this logic design flow is applied in FPGAs. So design entry and schematic capture, this is what you see in your laboratory sessions. And we do schematic capture or Verilog or HDL, VHDL coding. Then we can define the syntax and the connectivity check, and we can do a constraint. So the timing, the pin mapping, depending on the FPGA type that we are using, we have to map it inputs and the outputs and so on. And we do a place and route. So we put a logic design onto an FPGA fabric, and we have to route it through the inputs to the outputs. And then we can do a timing simulation. So we don't have a clock over here, but we have propagation delays. So how fast this input A is going to go through the circuitry, and you can see a change in the output. That's the propagation delay. So we have to do those timing simulations. And then once we are okay, we can create a bitstream config file, which is specific to FPGA, and then we can download it. Now, we can download and we can verify the operation of our code. Now, in the last chapter, we have seen how multi-level circuits can be optimized. I'm just going to make a brief overview of that before we go further in. Now, if you can assume that we have got a K level instead of 2 level SOP, sum of products or product of some circuits, where K is the maximum number of AND OR gates in the path from input to the output. So we are actually talking about the stages. Now, if you consider this function G, what do we have over here? We have got ABC, which is this one, ABD, which is this one, and we have got E individually or together, ACF and ADF. Now we have got 1, 2, 3, 4, 5 gates. We have got 13 literals. So how do we count that? 3, 6, 9, 12, and 13. That gives us 13 literals. And the 17 gate inputs, we have to count all those. 3, 6, 9, 12, and plus 5 over here. Total 17 gate inputs that we can have for function G. Now, the question comes over here, like in the previous chapters. Can we optimize further? Like, if we are going to optimize, can we consider more than 2 levels? Because this is level 1, this is level 2. Can we have more than 2 levels and be more optimized as a logic gate, number of gates and number of literals? Let's try. So let's write the equation first. G is equals ABC or ABD or E or ACF or ADF. Okay, now how can we simplify this? I can see that ABs are common over here. I can take them out. I have got C plus D or E, or at this point, A and F are common. So I can take A and F out, and I'll have C plus D. Now, what I can see over here, I have a common gate, which is C plus D. So rather than implementing them separately, I can use it, that one. Let's check if we have any other further optimization that we can get through this. Now, if you consider A is common over here, so I can take A out, C or D, and B and F can be combined together as a B or F or E. So this is what we can optimize it. Now, if we want to plot this compared to that, what are we going to get? We have got an OR gate, which is C or D. We have got an OR gate, B or F, and these three actually, because there's an A as well, are all OR together and together. Okay, so this is this part, and then they are all ORed with E. Okay, now let's count them again. Gate 1, 2, 3, 4. 4 gates. How many literals? We have got 1, 2. So literal 1, literal 2, literal 3, 4, 5, and complete all together as 6. So we have got 6 literals. How many gate inputs? How many gate inputs do we have? We have got 2, 4, 7, plus 2, 9. So we have got 9 gate inputs. Now, is this optimized compared to this one? So 5 gates, 4 gates, 13 literals, 6 literals, 17 gates, 9 gate inputs. Now we can see that this is more optimized, but when you consider as a delay wise, which I'm going to draw that with a green line, so from C to down to the output, actually, that is the longest path that we have. As we are having a 3 stages, stage 1, stage 2, and stage 3, we are actually increasing the delay. As we are decreasing the area and the cost of the logic, we are just increasing the delay. So we have to be really careful when we are optimizing these type of circuits. If there's a trade-off, are we looking for an optimization based on the area or based on the performance? Because the performance is degraded over here, but over here performance is better. But as a cost-wise, 3-stage logic is more economical. Okay, so this is something that we need to consider when we are doing logic design. Okay, one another interesting gate that we use in logic design, you already know buffer. Now buffer is a circuitry which you can have A on one side and Y on the other side. Y is equals A. It's like copying the same input actually to the output. If you put a bubble, it becomes inverter. So buffer is just keeping the same value, which is like a simple memory element. Now, there is another version of this buffer, which we call it 3-state or tri-state. So this buffer has got 3 states. That is why it's called 3-state. So we have got A, and we have got Y, let's say. This buffer has got another input, which we call it enable input. Now this enable input it's like a control input for the switch. So think about it as a switch. Let's say this is E, A, and Y, if I want to create a truth table. Now when enable is 0, it's actually the switch is open. So maybe I can create the switch over here. Okay, so you can imagine that there's a switch inside. Now when E is 0, no matter what's happening, so that's why I put don't care over there, the output, you're not going to get any output. We call it high impedance. It's not 0, it's not 1. Then, if I change that E to 1 and A is 0, whatever you have got on A, it will be copied to the Y. And if E is 1 and A is 1, then it's going to be 1 as well. So this is, as you can see, 3 states. State 1, 2, and 3. We can use these 3-state buffers and we can implement some other logical functions in logic design. So, for example, we can use them as an input-output on the same pin, so two-way communication. Now, E1 and E2 is actually deciding which one is going to be setting the I/O pin, okay? So if this one is enabled and this one is disabled, then this is going to X1 will be fed into the input 1. Or if this one is enabled, X2 will be fed in. Now we have to make sure that we don't enable them at the same time. So we need to create some kind of protocol. And multiple drivers are also doing the same thing. If you want to drive the same bus, E1 and E2 has to decide which one will drive the bus F. And once again, we need some synchronization elements over there so they won't turn on at the same time. Okay. Now, functionally complete set of logic gates. What is it? Now, we can say that a set of logic operator is said to be functionally complete if any Boolean function can be expressed using the operators in the set. So if you do remember from chapter 2, this is like we had these binary operators and we had some variables and we need to have that set and that set has to be closed based on the output that we are getting. So this is what functionally complete set of logic gates are. Now, what are those gates? OR gate, AND gate, inverter, sum of product, product of sums. AND gate or NOT gates, they're all functionally complete gates. So if you do any operations, for example, x plus y, which is x plus y prime prime, primes can be cancelled, or x prime dot y prime, and then prime again. These are all functionally complete set of logic gates, okay? So with these equations, we are actually ending up with a equation which is giving us a solution to that element of that set. Now, we also consider the NAND and NOR implementations, which we have said that they are universal because we can actually use NAND and NOR gates and we can implement any gate, inverter, AND gate, OR gate, and the same applies for the NOR gate when you can implement an inverter, AND gate, and OR gate. Now, if you have an AND OR inverters, like a typical sum of product, we can replace each AND and OR gate with a NAND and NOR gates and inverter equivalent circuits, which we can also optimize it using that. If there are same inverters on the line, they can be canceling each other so that you can just have a wire. So you don't need extra gate over there. Now, I just want to revise it with a simple function so that we can just review it. And we can also have, like, which we are going to see later on, single inverter can drive 3 lines, but you might have some degraded signals. Okay, so this is called Fanin. Now, in order to have just one inverter driving 3 different wires, you can have small inverters driving individual wires. Okay, so these can be all possible. Okay, so implement the following function with NAND gates. Now, this is a expression or a function given to us, and AB prime C or AB prime D prime. So AB prime is common and or EO here. So this is a typical implementation of. Now, how can we reduce that? Now we can replace each of these. We can replace each of these AND gates with a NAND gate. Okay, so this AND gate, it's going to be a NAND gate, which is AB. Okay, then this AND gate, it's going to be replaced with a NAND gate, which is AB prime in this case, which we already got that, so you don't need an inverter over here. And then that will be ended with C. And then we have got another AND gate over here, which is also AB prime. So I can get this input, fit it over there, and it has to be D prime. So I'm doing that part. So D, and I need an inverter to make it prime. And then we also have E, which all of those are going to be combined with an OR gate. So AB prime C, and AB prime D prime, and we also have E. Now, rather than having an OR gate, this will be replaced with a NAND gate. So either you can have it as AND invert, or you can have invert OR, which we will implement it both ways. So this will be our F. If you want, you can check it. This is A dot B prime. This is A dot B prime dot C prime. And this is A dot B prime dot D prime prime. And this is E. Okay, so we can easily get all of those, and then A dot B prime and A dot B prime dot C prime and A dot B prime dot D prime prime and E, and then we have got a prime of this. Now, as these is going to cancel that one, and cancel that one, then we can end up to a logic which is AB, but these are going to change from dot. These are all dots, dot to plus, plus AB prime, but C, or AB prime dot D prime, or E. That's it. We are getting the same result. Now, if you are doing that, you can also create a in-between stages. So you can take it as a inverters, which you can see that inverters are going to cancel each other, and then you end up the gate that we are having. Okay, so you can actually directly go from that one to that one. You don't need an intermediate stage, but this is also shown over here. We can do the same thing with the NOR gates. So the same function, but this time, rather than using NAND gates, we can use NOR gates. So for the AND gates, we just need invert signal. Okay, and we can actually have as the inverted and NOR gates to implement an AND function. So this is inverted, and we have got NOR gates. And each of those are also need an inverter because this is AB. Then we have got a NOR gate which is feeding in. C also needs an inverter. This is also inverted, and this part is also OR together, which is getting the same input. And we have got D because D is already prime, so you don't need to have an inverter over there. And then they're all combined together, which is NOR gate with an inverter and E over here. So all of these together is implementing this function as well using NOR gates. This is function F. Again, you can use this as an intermediate step. Okay, so we have done our revision about it. We know the NAND gate, NOR gate implementation. We know the tri-state buffers. Then we can move to the next section.